Today we're going to go over how to derive the volume of a square pyramid. Okay, so over here I have a picture of a square pyramid, which means that it's a pyramid with the base that is a square. So what is a square pyramid though? Like, what is it made out of? So a lot of people will tell you it's just a bunch of squares stacked up on each other to get to the point over here where the area is 0. So it's just going from biggest to smallest, which is basically 0. But the thing is, if you were stacking a bunch of squares on top of each other, a square is a 2D figure, right? So if you're stacking it on top of each other, you're really getting nowhere because it doesn't have a height, it only has a length and a width. So that definition is technically wrong. So for the height to be increasing every single time you put a so-called square on top, it should be a 3D figure. So that's why it is not a square. You can consider it a square because the height is so infinitesimal, but it is just a bunch of prisms with an infinitesimal height that are being stacked on top of each other to create this square pyramid right here, but the side length of each square is slowly decreasing to the point to where it gets to 0. And 0 times 0 is equal to 0, so the area over here, so the smallest point over there would be 0. Okay, so now let's get to calculating the volume of a square pyramid. Over here, I defined a few variables. So I defined the total height of the square pyramid as uppercase H, and I defined the side length of the square base as uppercase S. And then I put a line over here. So let's say you take a line, right? And that line is dividing the square pyramid. Okay, and after you divide it, you get a smaller pyramid, right? So for now, let's just focus on that smaller pyramid. So in that smaller pyramid, you have another square at the bottom, right? So that's your base. So that base, the side length of that square base, I defined that as S. And I defined the height of that cone, or not the cones, the square pyramid, as lowercase h. Okay, so now what we can do is we can solve for s in terms of everything over here. So we can say this. Because, okay, so let's use some geometry again. Over here, we have two triangles. We see that, right? So this is H and then S and then uppercase H and then lower uppercase S, okay? And we have two triangles, and we know both of these triangles are similar to each other because of the AA Similarity Theorem, right? So these two lines over here and over here are, oh, you can't see my cursor. Okay, so these two lines over here and over here are parallel to each other. So that means that this angle right here and this angle right here and this angle right here and this angle right here are congruent. So this one to this one and this one to this one, right? So that means that these two triangles are similar. And because of that, we can use a few proportions. So to start off, we can say S divided by lowercase h is equal to uppercase S divided by uppercase h. Okay, and I said we wanted to get a function in terms of lowercase s, so we can say s of h is equal to s divided by h multiplied by lowercase h. So if you don't understand what happened here, we just multiplied by h on both sides of the equation, right? So we did times h and times h, and this, they cancel out, so we get s of h. So it's just a function of h, because this is a constant, remember? The side length of the base, so the side length of the total square pyramid base is set, it's just s. And the total height is also set, it's just h. So that's why this is a constant, and this whole thing is a function of, so it's s of h, okay? So over here, we have one of the side lengths as a function of h, and let's go back to calculating the volume, right? So we know the volume is just the integral of the cross-section area A of x multiplied by an infinitesimally small thickness dh, okay? So the h is the height, and it's just infinitesimally small, and it's just a bunch of those squares with decreasing side lengths stacked up on each other to get this square pyramid right here, right? And because we are adding those those volumes, right? So technically it's a volume. So because we're adding those up together, we are basically adding the areas of a really thin prism. And because each prism is so small, we can think of it as a square. So over here, so if that was a little confusing, let me do that again. So S of H square is equal to A, right? So let's say A of H, okay? And this is our area, so this is our area, and we get S of H squared. And we know that V is equal to, like I said before, so let's just erase this and write it again. Okay, so erase that, and let's erase this for now. Okay, so you could write that down, or I'm going to write it down here again. So S of H is equal to S divided by H multiplied by small h. Okay, and over here we know that the volume is equal to the integral of A of H dh, because we're integrating with respect to h, and we know our limits are, so over here we start from the base up, right? So from the base our height is equal to 0, so we set our bottom limit as 0, and at the top of our square pyramid the total height is uppercase h, so we'll set our limit as 0 to uppercase h. Okay, and over here what we can do is we can substitute our S of H over here. So we just say V is equal to integral of 0 to H, and then S of H squared dH. Okay, so what I wrote over here, as I said, just S is a function of H, right? But S over here, so if you wanted to, you could have just written this as lowercase s squared. There's really no H variable over here. So what we need to do is over here we solved for S in terms of lowercase h, so we can substitute that over here into our equation. And we get V is equal to integral of 0 to uppercase h, and we do S divided by h. You have lowercase h there, so you're multiplying it. Now we have to square the whole thing, and then dh. So you can use a little bit of algebra. You just say 0h, and then s squared h squared divided by uppercase h squared dh. Okay, so if you remember from what I said before, I said that uppercase S is a constant and uppercase H is also a constant because they're set values. Uppercase S is just the side length of the base of the whole entire square pyramid, and uppercase H is the total height. So those aren't really changing. And because it's a constant, we can take it out of our integral, right? So we can just say V is equal to S squared divided by H squared integral of 0 to H squared dH. And we know from our power rule that the integral of H squared would become V is equal to S squared divided by H squared, and then H cubed divided by 3. So we just used our power rule. Okay, and now we have to substitute our limits. So we set it from 0 to h. So let me actually erase this so that we can put our limits there. Okay, so we do that and that. Okay, so we have 0, or let's write it on the other side. Okay, so you have 0 and h. So now what we have to do is we just have to substitute these because they're just our limit, right? And because it's 0, you know that, well, if you substitute it, it's going to become 0, right? So we can say V is equal to S squared uppercase H cubed divided by 3, and then you have H squared, right? So, and then you have minus, well, you substitute 0, so S squared, and then 0, so divided by H squared, and then 0 cubed divided by 3, so this cancels out to 0. and then you get your final answer of the volume of a square pyramid is equal to, so these two cancel out, right? So you get s squared h divided by 3. And if you did read before in your class or anything, you know that the volume of a square pyramid is s squared uppercase h divided by 3, or this is also equal to 1 over 3 s squared h. So that is how you derive the volume of a square pyramid. Thank you.